Good afternoon.
Good afternoon.
So, how's everyone today?
All right. Really great.
So, did anyone do anything amazing over the long weekend?
We hosted a robotics competition this weekend and it went pretty well and it was really fun.
Oh, okay. Yeah, that's right. So, but you weren't competing in it though, right? Or were you?
No.
No, we weren't competing.
Oh, okay. So, but it worked out pretty good? Had a good time?
Sorry, I didn't hear your question.
I said, but you had a good time and it went really well?
Yeah, I did at least. I don't know about everyone else, but it was fun.
It was so much fun.
Cool. All right, anybody else? All right, let's see. Who are we missing in Mogollon?
Just Rhett today.
Just Rhett. Oh, that's right. Yeah, he told me he was going to be gone. Okay, so the good news, I guess, is that so the curve on the midterm, the highest score in out of you guys, actually you tied my morning calculus class. So the highest score was a 95 on the midterm overall. So that means the curve will be 5 points. So I'll go back in and I'll add 5 points to your final score on the midterm. Okay, your overall. All right. So I was happy with that. I hope we're happy with your score. Any questions, comments, concerns about that?
Why was the midterm so much easier than all of the other tests?
I don't know. I probably because, well, actually, I know part of it is that I went through and like if there was 2 questions, I actually took the midterm from, I think there were 50 questions initially down to like 30 questions. So I think I probably got rid of a lot of the hard questions. So sorry if it wasn't challenging enough for you. But
That's what we were happy with it, but
yeah, no, I plus the other idea is that there have been some of the tests where you guys have had you've struggled to finish. And I wanted to make sure that each hour of the midterm, you were able to finish the 15 questions. So that's part of it too. So, because where you only had one attempt, I didn't want it to come back where, that was a real issue. So I did kind of try to make it a little easier, but I did want to, it included a lot of the stuff. There was a lot of material in it. And it probably was easier, but I would rather do that than have it be 10 times harder than what we've been doing. So anyway, so I hope at least you're happy with your score, and I hope it raises your grade, and I hope that when you look back at it, I kind of hope that you think also you've really learned a lot here in the last couple of months as far as calculus goes. I've sure been impressed, and I think you guys are a good group, and I think that helps too. So anyway, so 5-point curve, and so I'll be putting that in, and then your overall grades will go up a little bit. All right.
Okay, so Mr. Strong?
Yes.
There were 2 questions on the test. One was from section 4.3, I think, and the other one was from section 3.8, but it was from the section of 3.8 you told us to cross out because we wouldn't need to use. So how does that work?
Okay, so the do you remember are you talking about part 1 or part 2 of the midterm?
The one from 4.3 was on the first midterm, and the one from 3.8 was from the second midterm.
Okay. Are you talking about the 4.3 where the one about increasing and decreasing functions?
Yes.
Okay, so that one we did in 4.3 as far as using the derivative to determine that, but we also did that in chapter 1 graphically, where we graph the functions and you can see where the function is increasing and decreasing. Now the second one, what did you say it was from midterm part 2?
Yes. And it involved, I think, a sphere, if I'm correct.
Okay.
And the volume of it, and then involved the surface area, and yeah.
And what was the problem on that one?
You had to use one problem to find another problem to find the solution, I think.
The volume of a sphere is increasing at a rate. Find the rate of change of its surface area
Yes, that one.
when its volume and so what's your objection with that problem?
You just told us we wouldn't need to know how to do that one, and then so we crossed it off. We didn't go over it. We don't know how to do that one, and then it's on the midterm, and that's just kind of hard because none of us, I think, knew how to do it, and because of that, some of us may have missed it if we didn't guess right on it or do some weird way to do it.
Okay. So 3. Let's see. I'm trying to see.
Oh, it is. Mr. Strong,
Yeah.
while you're looking up that, I'm gonna reboot us because we can hardly hear you.
Oh, okay.
I don't know if it's on nobody's answering any technical support, so I'm gonna restart real quick.
Okay.
Shouldn't take too long.
Okay. Okay, so the rest of you help me out. I didn't start any on 4.4, did I?
No.
Okay. All right, that's kind of where I thought we were. All right. Well, so let me just talk for a minute. I mean, I guess it was the last part of 3.8, related rates in algebra, that we did skip that. Basically, we skipped it because the the problem that I had done for that involved several problems in it was some issues in geometry, okay, and similar triangles, and so that's why I decided I wasn't going to go to that. But see, the day before when you're asking to review, we actually went over a problem where we had to use, I think it was a related rate involving cylinders and cones. And so, because I spent like 20 minutes on that, I kind of feel like that I'm not going to throw that question out, because those were formulas that were, I mean, that problem was one where it was formulas in the book that you could take the derivative of. And it was easier than the one that I went over the day before. So I the one that I skipped on the notes was a kind of a different type of problem, but I could see your confusion. But if there was no curve at all, I would probably give you points for that. But that's why I do a curve, is if there's ever a question where people don't, if I didn't prepare you adequately, or if it's poorly worded or something like that, that's why I do a curve. But I don't think that particular question was unfair, but that might be part of the 5-point curve. Okay? So, all right. Well, can you hear me any better in Mogyan?
A lot better.
A lot better. Okay. All right. Well, I hope that satisfies that a little bit. So, but I will update your scores anyway. So anyway, well, we want to go into 4.4 here today. We're talking about concavity and curve sketching. And so let's see, I want to, all right. So we're gonna, so this is section 4.4. Oh, let's see, also, let me just look at, so what are we taking quizzes on? Let's see. So let's see, we took the midterm last week. And we did. All right, hold up just a second here. I'm not. Let's see, where did we, oh, what were the last quizzes we took? Through chapter 3? We haven't taken any on 4, is that correct?
Yep.
Okay, all right. I just want to make sure of that. So then what we will do tomorrow is we will have quizzes on 4.1, 4.2, and 4.3.
And as like a middle day?
No,
Okay.
no, just in your regular quiz time. So I guess, so you tell me if this is wrong. Let's see, so Mogion's doing them all at 10:15 now, is that right?
No, just Jordan and me,
Okay.
and then everyone else right before class.
Well,
Right for class.
Miss Townsend may have changed that, so we need to talk to her.
Yeah, yeah, because she had sent me an email saying that she was going to try to change some times there. I don't know. So either 1:50 or 10:15. And then Winslow, were you guys before or after? Let's see. I have St. John's and Winslow from 1:50 to 2:50. Is that right?
Do it on Thursday.
So I'm not gonna be here tomorrow,
Okay.
and that just because I'm gonna be on a student council trip, so I might just be late to class.
Okay.
So I can't do it before, and then I have practice after class. Do you think we could do it Wednesday?
Yeah,
Or
tomorrow.
Thursday? Thursday.
Yeah. Yeah, just shoot me an email and let me know what time would work for you. But,
Okay.
So then, Skylar, do I set you up the regular time then?
No, I can't do it tomorrow either.
Okay. All right. So yeah, you guys just let me know
Thursday.
Thursday at what time. Okay. And I guess maybe we need to. So St. John's, are you guys?
Yeah, from 150 to 250 works perfect.
Okay. All right. And then I'll hear more from Miss Townsend, I guess. So okay. All right. Sorry, I switched the camera. I realized and was getting ready to teach when I changed that. So okay.
So Mr. Strong,
Yes.
we can do it Thursday at 9:30.
Thursday at 9:30. Okay. All right. Sounds good. So remind me tomorrow in class. Okay. And I'll try to have it already set up. Okay. So 4.4 concavity and curve sketching is what this is called. The idea is to be able to know some certain things about the graph without using the calculator. If I were going to entitle this section, I would call it the second derivative test, because now we're going to be using the second derivative to tell us stuff. Okay. All right. So first of all, let's talk about what it means to be concave up and concave down. So it says the graph of a differentiable function, y equals f of x, is concave up on an open interval if the first derivative is increasing on the interval. So like if the first derivative goes negative, 0, positive, then concave up. So the way I think of that is it forms like a little cup. That's concave up. And the graph is concave down on an open interval I if f prime is decreasing. So like here, the derivative would be positive, and then 0, and then negative. And so the derivative is decreasing, makes it concave down. So I just think concave down, it makes a frown. Concave up, it makes a cup.
Mr. Strong,
Yes.
I forgot I had a dentist appointment today.
Okay. Just get the notes and
Yeah.
I'll post a video. The guy was out of town or whatever. Anyway, I'm trying to get caught up on all the videos.
Yeah.
So
I will.
we'll try to do that this week.
Okay, thank you.
You bet. So when you see me like move my hand along the graph, what I'm doing is I'm sort of imagining like the tangent lines to the curve. So tangents to the curve. So this would be positive, negative, positive again. I mean, not negative, 0. So where the derivative goes positive and then to 0, then it's going down. So as the derivative decreases, you have concave down. Here the derivative is 0 and then is going up. So there's the derivative is increasing from 0 to positive, and so then you get concave up on that portion of the graph. Okay, so the second derivative test. Now, I'm not sure why, but somehow I left this off the sheet, okay? But you definitely need to put this in your notes or write it in the margins or something, okay? This definitely should be in your notes. So the second derivative test for concavity says let y be a twice differentiable function on interval I. That means you can take the first derivative and the second derivative. So if the second derivative is greater than 0, so that means it's positive on the interval, then the graph over the interval is concave up. If f double prime is less than 0, so in other words it's negative on the interval, the graph of f over I is concave down. So that's an even easier way to determine concavity. Instead of saying where is the first derivative increasing or decreasing, this is better. To say where the second derivative is positive, it's concave up. Where the second derivative is negative, the graph is concave down. So this is what we're going to use most of the time. And so this is called the second derivative test. All right? So here, like, let's say if this is our function, y equals x squared, and we want to know where is it concave up, concave down. Well, the first derivative is 2x. The second derivative is 2. Well, that's always positive. So what that means is this derivative is always concave up. Well, duh, this is y equals x squared. This is a parabola. We know it's concave up. But we're just using the second derivative to say, look, the second derivative is always positive there. So it's always concave up. All right? All right, go ahead and try practice one, please. All right, so Denon, when you've got the answer.
It's concave up.
Always?
Yes.
Yes. Okay? So when you take the second derivative, y double prime is 4. Always. Okay? So it's always concave up. Concave down, never. All right, any questions on that? All right, good. Okay, when denoting the second derivative, you can use the notations y double prime or f double prime x interchangeably. All right, so let's say you had y equals 3 plus sine x from 0 to 2 pi. And we want to know, where is this concave up? Where is it concave down? So when you take the first derivative, the derivative of 3 goes away. The derivative of sine x is just negative, or is positive cosine x. The second derivative then is negative sine x. Okay? So then if you think, all right, well, where is negative sine x equal to 0? So then you divide each side by the negative, and then sine x is 0 at 0 and pi. Okay, so now once you figure out where the zeros are, this is what you do on a more complicated problem. Then you do the second derivative sign chart. Okay? So you remember we did the first derivative test and we did the sign chart. And what that is you write where the derivative is equal to 0, you put those on the number line, 0 and pi. And now you test the intervals. Only you're plugging into the second derivative, not the function, not the original function, not the first derivative. So you say, okay, just pick a number between 0 and pi. Say pi halves. And you plug that into the second derivative. So the sine of pi halves, okay, think pi halves, the sine is 1. So that's negative 1. So it's going to be negative in that interval. Okay, then you pick a number between pi and 2 pi halves. So let's say 3 pi halves. So the sine of 3 pi halves is negative 1, but then you take the negative of that, and so it'll be positive. So then once you've made the sign chart for the second derivative, then you can say, all right, well, it's going to be concave down everywhere in this interval. where the second derivative is negative. So that would be between 0 and pi. And then it's concave up in this area where the second derivative is positive. So from pi to 2 pi. Okay? All right. So let's see if you can do practice 2 and make this sign chart for the second derivative. And see if you can determine where is that function concave up and concave down. So any guesses as to why I give you such big numbers on this one?
So we can't put it in the calculator.
Yep. Because I get to about this point and I have some people say, well, I don't really need this calculus part. I can just put in the calculator and tell where it's concave up and concave down. So this, it would be way more work to do it that way. All right, so Denon, when you've got it.
Is concave down from negative infinity to negative 10,000 over 3, and concave up negative 10,000 over 3 to positive infinity?
Yep. And so, as you said, negative 10,000 over 3, that's the same thing. So, good job. Okay, any questions on that? So, where the second derivative is negative, that's where it's concave down. Where the second derivative is positive, that's where it's concave up. Okay, so let's see. Okay, so a point of inflection is where the second derivative is 0 or fails to exist. Okay. Well, at a point of inflection, one of those things happen. Okay. So what you do is where the concavity changes is a point of inflection. And where you look for that is where the second derivative is 0 or fails to exist. Okay? So it's kind of like the critical points. Remember, the critical points are where the first derivative is 0 or fails to exist. And remember, the critical points were the candidates to find your local max and mins. Well, here where the second derivative is 0 or fails to exist, those are the candidates for our points of inflection. Okay? They're not guaranteed to be, though, because the points of inflection, the concavity has to change. If the concavity doesn't change, then it's not a point of inflection. All right, so let's say this says find the point of inflection for this. So what you do is you take the first derivative and then take the second derivative, okay? And so I get 10/9 x to the negative 1/3. Now, usually it's easier to deal with positive exponents, so I'm going to use the elevator rule and take that exponent to the denominator and then set it equal to 0. Now, you might remember, because we talked about this with critical points, is that a fraction, when you set it equal to 0, the numerator has to be 0. See, 10 cannot be 0. So there's nowhere where the second derivative is 0. However, if the denominator is 0, then the second derivative is undefined. And that still could be an inflection point. So what value for x would make the denominator go to 0 here? What value for x would make this denominator go to 0?
Yeah, 0.
0, because the cube root of 0 is 0 times 9 is 0. So 0 is my candidate for the point of inflection. So I do the second derivative, the sign chart, second derivative test. Okay? All right. So at 0, the second derivative, and you want to make sure you label it, second derivative is undefined. So I put a u there. All right? Now, I pick a, just like with the first derivative test, I pick a number in each interval and check it. So I pick a negative, and I want to do something I can do the cube root of, okay? Because I'm going to plug it into the second derivative. So I plug it into the cube root, so let's say negative 1. All right, the cube root of negative 1 is negative 1. 10 divided by 9 times negative 1, that's negative. So this is going to be negative. All right, now I pick a number bigger than 0 and plug it into the second derivative. And let's say positive 1. Well, the cube root of 1 is 1. 10 divided by 9, that's positive. Okay? So what this means is right here, it's going to change concavity. Because the second derivative goes from negative, where it's concave down, to positive, where it's concave up. So where it changes concavity at x equals 0, and I plug 0 into the original function, and I get 0. So the point of inflection, 0, 0, is where it changes concavity. So either minus to plus or plus to minus. It's still considered a point of inflection. Okay? All right, so go ahead and I'll leave this up for a minute. Go ahead and try practice 3. All right, so Rachel, when you've got it.
There are none, because it's always concave up.
So, if the second derivative is always positive, except where it's undefined, it doesn't change concavity. It's always concave up, so there is no point of inflection here. Okay? Great job, Rachel. All right. Any questions on that? So if there is no change of a concavity, then you have no point of inflection. All right, so inflection points occur where the second derivative does not exist, or where the second derivative is zero, or where it does not exist. And you can have more than one. It just depends on the equation. All right. So let's just see if you can find the points of inflection for that. All right, so Rachel, what do you think for that about that one?
Well, it's always concave down, so is there no points of inflection?
That is correct. Okay. So if it's always concave down, then there are no inflection points. Okay. So with concavity, if the inflection points occur where there's a change of concavity. So if there's no change of concavity, then there's no inflection points. Okay. Okay. So a point of inflection can occur at a vertical tangent to the curve where neither the first or second derivative exist. So that's kind of weird that you can have a vertical tangent that's defined at a point in the original function, but it's not defined for the first or second derivative. So let's look at practice 5. All right. So see if you can figure out the points of inflection here, if they exist, or if any of them exist. All right, Nathan, do we have any points of inflection for this?
1 at 0.
1. Okay. So let's see. The second derivative changes. Oh, it doesn't change. It's always negative. So let's see why that would be. Okay, did you get this for your second derivative? Negative 2 over 9x to the 4/3?
Yeah, no, I got all that, but I got the same sine graph, but the thing was I was just confused at what the thing before was saying. And so
Okay.
I was just putting something out there. Sorry.
Okay. So if the sign doesn't change of the second derivative, then there is no point of inflection. Okay. But what the thing was saying is, do you see how the second derivative here is undefined at 0? So is the first derivative. But it still could be a candidate for a point of inflection. So even though it's not defined, now it turned out that it wasn't for this, but it could be. It could be. Okay. So I'm sorry if that was confusing. All right. So, to study the motion of a body moving along a line as a function of time, we often are interested in knowing when the body's acceleration given by the second derivative is positive or negative. So that's kind of like what we've been doing. Is just like studying concavity is analyzing the second derivative. Here we're analyzing the acceleration, which is the second derivative. Where is it positive or negative? So if the acceleration is positive, then that means the body is going faster or speeding up. If the acceleration is negative, less than 0, then that means it's slowing down. It's decelerating, as we would say. All right, so let's look at practice 6. Says a particle is moving along a horizontal line with a position function S of t equals 3t cubed minus 15t squared plus 20t minus t. But this is only good for positive values of t and 0. Okay? Find the velocity and acceleration of the particle. All right, so, and then it says, when is the particle slowing down and speeding up? Okay, I don't see that on the guided note, so maybe it somehow got removed. But go ahead and find the acceleration function and then determine when is it positive or negative. Okay, so we're down to 1 minute, so we're going to have to start here tomorrow, but I would like you to finish this problem and we'll go over it first thing tomorrow, and we'll be able to finish 4.4 tomorrow. Okay. All right. Any questions before we call it? Before we drop? All right. Thanks, you guys. Have a great day, and we'll see you tomorrow. Okay. Have fun in your student council trip.